We proceed and go over phase equilibrium. Well, we want to understand colligative properties. Now, colligative properties of materials are properties which only depend on the concentration of the substance and not on its identity. And some of the colligative properties that we need to understand. First one is boiling point elevation. What of boiling point elevation? Now, when you are talking about two ways that we need to get to understand when we're talking about colligative properties is the solute and the solvent. A solute is something that has been dissolved. A solvent is what you have dissolved into. And so when we are talking about a solvent, in this case I'll be referring to water, because most you want to dissolve everything in water. And so what happens for pure water, we know that the boiling point is at 100 degrees Celsius. But when we get to add a solute, anything that can dissolve in water, for example, we add a salt or sugar, the boiling point of water gets to increase. Instead of it boiling at 100 degrees Celsius, it might start boiling maybe at 105 or something like 102 degrees Celsius. And so the boiling point has been elevated. That is the boiling point elevation. And so how do we get to calculate the boiling point elevation? So that is calculated by change in temperature is equal to Kb molarity and then multiply by the Van Hoff constant. So Kb here is representing the boiling point elevation constant. It is called molar boiling point elevation constant. So this is not molarity. It's not capital M molarity, but it is small m, which is molarity. So we need to get to differentiate this. Molarity, capital M, is found as number of moles over volume, but molarity, small m, is found as number of moles divided by mass. So here you are talking about the mass of the solvent, the mass of what you've, for the first one, molarity, you are talking about the volume of the solvent. For example, if you have dissolved sugar in 100 liters of water, you are interested in 100 liters of water. But in this case, you are not interested in the liters of water in which you've dissolved, but in the mass of water in which you've dissolved, and the mass should be in kgs. So that is the difference between molarity and molality. Now Kb is the molar, and this is not R because we're not talking about molarity, it is molar with L. Molar boiling point elevation constant. And the M here is what we are referring to as molality. Now I is referred to as the Van Hoff constant. What is really high? So when you're talking about non-electrolytes, these are substances which do not form ions when you put them in solution. For example, organic compounds. Organic compounds are examples of non-electrolyte. These do not form any ions. An example that I can give is sucrose, methanol, those compounds. So for non-electrolytes, the Van Hoff constant is equal to 1 because they do not disassociate. But for substances which form ions, for example, sodium chloride, if this disassociates, it forms sodium plus and chlorine minus. So we have got two ions here. So the Van Hoff constant is going to be equal to 2. If you are talking of, let's say, aluminum chloride, okay, aluminum chloride. So aluminum chloride, that should be a 3. Let me first talk about magnesium chloride. So when this disassociates, it forms magnesium 2 plus and also 2 chlorine ions. So we count the number of ions, we have got 1 there. In other words, we're adding up the charges, negative 1 charge and positive 2 charge. But we're not adding with the signs. All we get is, how many are there? We have got 2 charges, 1 charge, so 3 charges. So therefore the Van 't Hoff constant for this one is a 3. If we're talking of aluminium, let's say aluminium sulfate. If this disassociates, is going to give us 2 aluminium, 3 plus, and also 3 sulfate ions. So here the Van 't Hoff constant is going to be 5 because we have got 3 positive charges and then 2 negative charges. So that is the Van 't Hoff constant. Now we can consider a simple example. Let's say we've been given that, let's say 2 grams of sodium chloride dissolves in water in, let's say, just 10 liters of water. And the Kb for water, this is a constant. The molar boiling point elevation constant for water. So the Kb for water, that is 0.51. Calculate the new boiling point. But how do we go about such a question like that? We add 2 grams of sodium chloride in 10 liters of water, and we want to now calculate the new boiling point of water. So what we are going to do is, we are going to first determine the molarity for the sodium chloride. And how do you find molarity? We know that molarity is given by number of moles divided by mass. This is number of moles of solute, what you have dissolved, divided by the mass of the solvent, what you have dissolved into. So this is going to give us number of moles of solute. We have been given 2 grams of sodium chloride. How do we find the number of moles? Number of moles is given by mass divided by molar mass. So we need to get the molar mass of sodium chloride, and let me just check on the periodic table for the molar mass for. Alright, so sodium, it's first chlorine has got a molar mass of 85. Sodium chloride, chlorine, this is 35. Sodium, this is 23. So summing up this will give us 58. That is the molar mass. So the number of moles is going to be 2 over 58, and that is going to give us about 0.03448. That is it. This is in moles. And so to calculate the molarity, we are going to divide those number of moles, 0.03448 moles. But divided, where we are talking about the mass of the solvent, and in this case the solvent is water. We have dissolved 10 liters of water. I mean, we've dissolved 2 grams of sodium chloride in 10 liters of water. But how do we find the mass? We know that density is mass over volume, and so this will give us mass being equal to density times volume. Okay, this is mass, which will be density times volume. So that will give us mass being equal to, the density of water is 1000, okay, kg per liter, and then multiply that by, we have been given 10 liters. 10 liters. So this is going to give us 10,000 kgs. So this is the mass of water which we've dissolved into 10,000. So we'll go on and put that value in the denominator. So this will be over 10,000 kg. So just go on and divide the value on top with 10,000 in the bottom. That is going to give us about 3.448 times 10 to the power negative 6. Mole per kg is what we call molar, small l, not capital M. I mean small m, not capital M. If we use capital M, that will mean molarity. Now that we have got the molarity, we can now determine the change first in temperature. The change in boiling point, that will be Kb for water, that is 0.51. Well, the unit for Kb is given in degrees Celsius per mole. That's the unit. And then multiplied by, this is per molar, not really mole like number of moles, but molar, talking of concentration. So that is degrees Celsius per molar. Okay, and we are multiplying that by the molarity which we have found, which is 3.448 multiplied by 10 to the power negative 6 molar. And then also multiply by the Van Hoff constant. Now the Van Hoff constant, this is for sodium chloride. When sodium chloride is associated, forms sodium ion and chlorine ion. These are two. So we are going to multiply this value by 2, and that is going to give us, so multiply that by 0.51 and then by 2. So that will be 3.517 multiplied by 10 to the power negative 6. This is going to be degrees Celsius. So this is the change in temperature. Now to find the new boiling point is simply the original. Okay, change in temperature is given as the final temperature minus the initial. So the change is 3.517 times 10 to the power negative 6. What will be the final? The initial boiling point for water, we know that it is at 100 degrees Celsius. So we'll take this value the other side. And so the new boiling point is going to be that value found plus 100. And that will be about 100.0000035 at the end degrees Celsius. So really there is no change in boiling point when we add this kind of mass. Thank you so much for being present. See you in the next video. I will continue talking about other colligative properties.